Ukrainian and Russian social media with latent semantic analysis. So the study of Russian-speaking media space has become very important in the last days because of the full-scale Russian invasion into Ukraine. And with this report, we study whether LSA could make out for a good model for distinguishing Ukrainian and Russian media posts.
Okay, actually, what we did, we collected the data consisting of 146,000 Telegram posts. 40% of them are Ukrainian and 60 are Russians. Yeah.
And after we collected this huge data set, we have done some pre-processing. So because we are training a machine learning model, we have to make sure that our database isn't leaking. So a leaking is a process when our labels, which are whether a post is from a Russian origin or Ukrainian origin, are leaked into our data. So for example, we have a channel which always mentions its tag as a marketing text in all of its posts. For example, as you can see here, Trucha, right? So this channel mentions always its name. And so it would be cheating if a model learns that whatever channel prints Trucha at the end is a Ukrainian channel. This model won't work on new channels which mention names that the model didn't see while training. So removing cheat words like this, ones listed here on the image, is very important. The next thing we did was to remove short posts. So we remove short posts mainly because they usually don't provide many information. And limiting the shortest post we keep in the database improves our model's performance by a margin. And the last thing we did was to eliminate cheating, was to remove posts in Ukrainian, because sometimes our Russian language Ukrainian Telegram channels, they post in Ukrainian, and obviously we don't want the model to learn that a post is Ukrainian if it's in Ukrainian. That would be cheating, right? So we want it to learn the sense post conveys instead.
Okay, as Mikhailo has already mentioned, we were dealing with cheat words. So what are you seeing in this graph is a SVD decomposed matrix of vectorized documents, and the sentences of all our database are projected onto three principal axes, from the PCA. And PCA means that we choose such three principal components which have the biggest variance. Yeah, and as we can see, we have a guess that this tail right here is consisting of those cheat words which we were trying to remove. And after filtering those, we can see that the same database now is much more combined together, much more dense, I would say.
Now, after pre-processing, we have to choose a vectorizing method for our database. So obviously, if we have numeric methods, numeric models, numeric machine learning models, we want to have the database consisting of numbers, and so we have to transform the initial post consisting of words into numbers. So how do we do that? There are several methods to achieve this effect. And the simplest method is to just count which words appear how many times. And so this is what count vectorizer, or in other words, a bag of words, does. The count vectorizer simply counts the frequencies of all of the words of the post. Now there is a simplified version of count vectorizer, which is a binary count vectorizer, which performs a little bit better than count vectorizer. So basically what it does is even simpler, because it only says whether a certain word is present in our post and not how many times it is mentioned. And the most advanced and the most efficient version is the term frequency inverse document frequency vectorizer. So what it does, it scales the output of count vectorizer, which is this TF term here, and divides it by the inverse document frequency. So basically, if a certain word is mentioned in posts very frequently, it doesn't mean that it is important. And so its importance is actually measured by how frequently it is present in other documents. So for example, if it's present in all of the other documents, this word doesn't make this certain post unique, because this word is very common. But if a word is uncommon, we would have to scale its core so it's actually more important.
Okay, and you may ask, why linear algebra? Where is linear algebra here? Okay, as you have already heard earlier, we have used such three methods, mainly SVD, and on the top right corner you can see how we decompose our transformed matrix of database onto word space scaled by some constants, meaning singular values, and then multiplied by document space. PCA were used to kind of see in which directions our document has the biggest variance, and non-negative matrix factorization were kind of similar to SVD but performed poorly.
Yeah, so other than studying what methods perform better in terms of matrix factorization, we could also compare our resulting models to some other classical ML approaches. One of them is k-nearest numbers clustering. If we choose k, which is the optimal k for in our case, to be 2 to 4, and we use the scaling distance, or if we would use a naive bias classifier, treating each word as an independent influence on the entire post, we will get an accuracy of 70 to 76%. Now, the only model we tested which performs better than our model, which uses LSA, is a logistic regression. It actually performed 5% better, showing the score of 90 to 95% depending on the tests.
And finally, on this graph, you can see the comparison of our kind of custom LSA algorithms comparing to logistic regression. So the line in blue is latent semantic analysis. And as you can see, as the border of the shortest message, meaning like we throw out messages which are shorter than, say, 100 characters, and we see that our latent semantic analysis shows a result of 85% and logistic regression 91%. But as the message length of messages grows, our latent semantic analysis really gets closer to the logistic regression. So at the 1000th point, they are really tied together. The difference is only 1.5.
Yeah, so at this point, thanks for your attention, and leave us a good mark if you liked our project. Thank you.